Hi guys, welcome back. So I want to carry on with the harmonic oscillation. Oh, yes. And we did the classical part where we saw that an harmonic oscillator basically think about a spring with a mass on a wall or a pendulum. Yeah, hang on the wall. The pendulum swings and motion the position. The position of the mass can be described in some reference frame, whatever you want to call it, as a sinusoid. Okay, and it's called harmonic because, I mean, if you think about even in music, those are harmonics like notes. Notes vibrate at certain frequency, so something that vibrates at a certain frequency, those frequencies are called harmonics. Okay, so harmonic oscillation, but we if you remember, we discussed about the Hamiltonian approach a little bit, not in detail of course, but we wrote the Schrödinger equation like this way, and like this way, and we remember that the Hamiltonian is a function, something, let's say it's an operator, but let's say a function that has two numbers like these ones, and these are constant that depends on the mass and on the force acting on the system. So if it's a spring, it could be the elastic constant here, the mass is here as well, but the important thing is that it's a quadratic, so there are two squares here, the momentum and the position square, and this makes the interaction like harmonic. What I want to show you, so we showed that in classical physics this leads to sinusoid and cosinusoids, which is fine. What I would like to show at some point, not in this set of slides unfortunately, because we need a bit of math and tools to get to the quantum solution of this equation for the harmonic oscillation. I don't want to rush it. I don't want to give you already the solution. I want to do a couple of steps. But definitely last time we talked about this uncertainty, this relation. If you remember, we said that whatever we call P and X, they must satisfy this equation. These are two operator matrices. They do not commute. If you remember, numbers commute always. A and B minus BA, if they are numbers, it's always zero. Doesn't matter which number you put in, it's always zero. But as soon as you step out of numbers and you can think about matrices, for example, and you pick these two matrices as an example, A and B, they do not commute. So this would not be true for matrices. Also, we showed last time that since we're dealing with function, psi is a function of position and time, this Hamiltonian operation here needs to be acting on functions of space and time. So this operator here, x and p, must be something that acts on a function. And last time we saw that x would work as a multiplication of the value of x of the function psi, and the operator p works as the derivative of that function with respect to x. Now, I did try to convince you with a simple example that on a function that these two operations do satisfy this condition here, which as a consequence satisfies the uncertainty principle, the Heisenberg uncertainty principle. Okay, which tell us that you cannot measure precisely at the same time position and momentum for a particle. There are many variations of this. You can recast it in many ways, but in essence it means that you cannot know. Essentially it does say that clear trajectory for a particle do not exist. You never know what happens from one place to another. There are jumps, they are called quantum jumps. But anyway, let's not get in details. I want just to follow this line of reasoning. But what I want to do today is introduce a bit more formally this operation here, x and p, in order to exploit or touch upon an argument that is very crucial in quantum mechanics and also in classical physics, which are the symmetry of a system. Okay, what I want to show you today with the math that we developed so far, I will try to keep it light, but as you will see, I will touch upon derivatives, exponential, complex numbers, and I will put everything together to give you an idea of why we can say that, why it's fair to say that the momentum operator, for example, p over the function psi, is the derivative of x over psi, x and t. Now, one thing that I want to say, as I said, about symmetry. Okay, think about physics, mass and object here, position x0, and you do some experiment on this object. It shouldn't change anything if the position of this object would be done in a different place on Earth. Of course, we need to be careful when we say these things, because if you realize that any place on Earth has different, for example, acceleration due to the position on Earth and the rotation of Earth, if your experiment is sensitive to that particular effect, then this is not true. But think about in your room, if you do an experiment on a side of a table, and then you do the same experiment at the other end of the table, I don't see why it should be different in any reason. Anyway, even if it's not true, or if it's true, it doesn't matter. We can always think about the possibility of having these properties for physics and see what happens next. So we can enforce, if you want, that the physics must be the same in different places. By the way, this is very closely related to Galileo relativity principle. So we want to go against Galileo, not today. So let's say we accept that the physics is the same in two positions. Okay, but that implies some things on the structure of the function, because that implies that your wave function psi in a position x and t must give the same results when you apply movement, let's say translation, rigid movement of your coordinate system from one direction to another. And let's see what this leads us to. Suppose we have x prime of t, which is the new position, which is very close to the initial position by a very small amount, epsilon. Let's forget about t for a moment. Oh no, okay, we keep t. Okay, doesn't matter. Okay, it's very close. Okay, now if you remember the definition of a derivative, what is the definition of the derivative? Which is the definition of a derivative? If you do derivative of x of a function f, we can call it f of x plus h minus f of x divided by h, and then we take the limit. Okay, so but if we think that these are like big, like not infinitesimal, we can say that this is true, and then we can take the limit of this expression for h that goes to 0. But now look here. Okay, this is very much like this guy here, right? F plus h, if I drew h in. Okay, meaning that if we rewrite this expression here, we already have the solution, right? Let's see if I can do this quickly. We just rearrange the term that we know already. We call f psi, okay? Psi of x of t is equal to, so we of f of x plus h minus d, sorry, this is a psi, we said to keep it psi, d psi dx psi of x time h, okay? And we see already that this is our, sorry, this is f of x, this is f of x plus h, and this is f of x. I got a mistake, sorry. Now plus h. Yes, fantastic. What does this mean? I mean, it means that we can carry on. It means two things. So we have we have an expression that tells us how to move from psi dx to the translated version, and as you can see, the derivative appears already naturally. But this is not enough, or it could be enough, but we want to do a bit more. We want to keep doing this expansion, and then we can apply many orders of the derivative, because basically this expression, if you remember the power series, this can go on and on with infinite terms. Okay, if you remember, you can write any function with infinite terms, and each of these is a derivative. So we can x plus 0 is equal to psi plus a derivative of x psi of x plus derivative square of x with the factor of 2 factorial plus derivative cube of x, sorry, derivative cube, and so on and so forth, with many orders for our derivative. And all of these are derivatives: square, derivative cube, derivative cube and fourth, and so on. And if you remember, this is also very close to the, if you collect psi of x, this is acting like then 1 plus the derivative of x plus derivative square of x plus derivative of I of x cube, and so on to the n and to infinity. Apply to psi of x. Okay, so there are all of the derivative in order and psi of x. Okay, so we can kind of, I'm skipping some steps here, but basically we are reconstructing. So what we are doing is we are building up a series of operations on x, and this can be seen as the exponential of the operation of the derivation, because if you remember, the exponential is the sum of x and n factorial. Now, if we replace then x with the operator p, and h is the small distance that we travel, we put p h here, and we get this expression. So we can say that our translated function is somehow related to an expression which is e to the derivative of x h, which we call p, right? E to the I p of h on the function of over the initial function. Okay, so this is nice because we just showed that these well, I skipped a few bits in the term, but anyway, this is the essence of it. So we use the derivative, we use all the orders of the derivative, we reconstruct the exponential function out of all these derivatives using this formula here. We remember there is a complex value like so that is needed because we are dealing with complex functions, and this means that we have this expression. Now the only thing that we need to prove is that this value here, which is the translated version of this value here, gives the same result of the initial function here. Otherwise we are doing different physics in different positions, and we don't want it. We do this one quickly, and then I will wrap up for this video. And I will I will do one other things that I want to show you before moving to the harmonic oscillator in the quantum domain. So let's see that this physics is the same, and to do that we just need to remember one thing. So suppose we have a complex number e to the I phi times e to the minus I phi. If you remember, we can do it. This is cosinus phi plus I sinus phi times a complex conjugate cosinus phi minus I sin phi, and this is exactly, if you do all the terms, it's cosinus square plus sinus square, which is 1. Okay, this is always true. If you have a number times complex times its complex conjugate, this is 1. This is a definition, if you want, of the complex conjugate. Why I'm saying that? Because if you think about what we just saw, the translated function, the function that we have in a different location, the wave function in a different location, which is psi of x plus h, we said that is equal to the exponential I p h, let's keep h, psi x. Okay, now let's do psi h plus h times the complex conjugate of this one, like so, complex conjugate. And why I'm doing this? Because this expression here, if you remember the video on the complex number, is exactly the modulus square of x plus h, exactly the modulus square, which is the probability, which is the physics of it, right? Wave function gives a probability. So let's do this, but using this function here. As you can see, if we take the complex conjugate of this one, we have exactly what do we have? We have exactly what do we have here? Right here, we have e to the I minus I p h times psi of x e to the I p h psi of x, complex conjugate here. But this is clear now that these two operations here are like the complex number e to the I phi to the minus I phi, which is 1, and in fact they cancel out, and you're left with the complex conjugate of x, of psi of x and x, which is exactly the modulo square of x. Okay, meaning that this one is exactly the same as modulus sine of x squared, which is good because it means that the symmetry over translation is preserved. If we use this operator P as written like this with an h bar as a derivative over x, okay? Now, since we now are confident that this is a very good definition of an operator because it represents a symmetry of the system and it gives us the correct translation, and in fact it makes sense. If you want to move an object, you need to apply momentum, right? For example. Anyway, but what I want to say is that now it's easy to remember that find x and p, because now we have this p is done, so x can be just a multiplication of x, as I showed you last time. Last bit that I want to do is to show you one thing. Consider this expression, a plus ib and a minus ib, complex number. This is a square plus b square. We can do it because it's a square b square plus b, e b a, and this is exactly a square plus b square. Okay, this is fine. This is fantastic. This is fantastic. This is fine. This is fantastic. No, what? Sorry, that's not part. Yes. So why I want to say that? Yes, because if you remember, the Hamiltonian is something like p square plus x square, right? And let's try to write it in this way then. We can write the Hamiltonian. We can do it, right? Because why not? I will show you why we want to do it in the next video when we will solve the harmonic oscillator, because this is a quick way, well, a quicker way, to solve it. We can write these, so we have a plus ib times plus ib, it's, we said a squared times b squared, meaning that h can be written as x plus ip times x minus ip. Okay, this is x squared plus p squared, because it's the same structure. You can prove it. Apart from the fact that I forgot, of course, that there is the commutator plus h identity, because in this case here, a times b minus ba cancel out. In this case here, x times p minus p times x do not cancel out, and they give the identity. So you have this extra term here, but we will see what this does to the system. So what I'm saying is that if we introduce these two operators here, which we'll call a dagger and a, we can write this equation here, which is very close to the initial Hamiltonian. Let's say call it h bar. Okay, and I will show you that these are very important operators, ubiquitous in quantum mechanics, and we will use them to solve the equation. They're called creation and annihilation operator, or modes operator. Anyway, enough for today. What I want to just to recap quickly what we said today, which is that we have symmetries, translational symmetries, and then we have an operator P, which is the generation of the translational symmetry, and it's exactly the derivative of x plus some constants and a complex value, and this leads to our displaced function here, okay? And this can be written as e to the I p of h psi of x, psi x plus a, where p is, we understand now, h bar dx. Okay, and I just realized that I use h and h bar in the same one. Let's call this is anyway, this is h, this is like x, if you want, x is 0, and this is h bar, the Heisenberg constant. Sorry for that, but I hope it was clear, because I use h as a displacement as well, not as the Planck constant, and h bar as a Planck constant. But anyway, this is the operation, this is the translation. We show that they have the same features because the probability is conserved, because psi and psi is 1, but also psi h plus and psi h plus is 1, by using this fact that we know from a complex number here. I hope that makes sense. Hope you liked it. I will put some links, and next time we will tackle the harmonic oscillator in the quantum regime with this new operator A dagger and A that we introduced, which are x plus IP and x minus IP, which are very important operator in quantum mechanics. Okay, see you next time. Bye bye.